All right, let's dive right in. We're going to talk about one of the toughest nuts to crack in the whole energy transition, heat. And I don't mean just heating your house. We're talking about the heat for entire cities, for massive industries. And the answer might just be found inside some truly giant machines.
So here's the deal in Germany right now. The vast majority of heat that keeps buildings warm and powers factories, it comes from burning fossil fuels. We're talking mostly natural gas and coal. And that, as you know, is a huge source of carbon emissions.
Which, of course, leads us to the massive multi-billion-euro question, how on earth do you break that dependency? How do you decarbonize heat for an entire country? Well, the answer everyone is looking at is this, Großwärmepumpen. It translates to large-scale heat pumps. And you've got to forget the little box you might have for your house. We are talking about absolute giants, industrial-scale machines made to plug right into city-wide heating grids. This is seen as the key technology.
And look, this isn't some fringe idea. The projections are, frankly, wild. This chart shows the plan, and it's an incredibly ambitious one. By 2045, these machines are expected to go from being a pretty small contributor to the #1 source of heat for Germany's cities.
Let's put a number on that, because it's a big one. The target is for these giant heat pumps to supply almost 60% of all district heat by 2045. That's not just a small change. That's a complete overhaul of a nation's energy infrastructure.
Okay, so how did these things actually work? Well, the easiest way to wrap your head around it is to think of your kitchen refrigerator, but running completely in reverse. Instead of pushing heat out of the box to keep things cold, it pulls heat from the environment and pushes it into a heating system to make things warm. Now, to really get this, you need to know about something called the coefficient of performance, or COP. It's just a simple measure of efficiency. It tells you how many units of heat you get out for every 1 unit of electricity you put in. So if a heat pump has a COP of 4, that means for 1 kilowatt of electricity, you get 4 kilowatts of heat. The other 3 are pulled from the environment, basically for free. That's the magic, right?
Let's just quickly walk through the cycle. First, a special liquid, a refrigerant, pulls in some low-grade heat from, say, a river, and it boils into a gas. Second, a compressor, powered by electricity, squeezes that gas, which makes it get really, really hot. Third, that super hot gas now flows past pipes for the city heating network, releasing all its heat and turning back into a liquid. And finally, that liquid goes through an expansion valve, which makes it super cold again, ready to start the whole cycle over. It's a continuous loop of, well, thermal upgrading. Pretty neat.
So with that kind of potential, you can probably guess what's happening. The market for these things is on fire. Demand is just exploding, and the technology itself is being pushed to its absolute limits. I mean, just how fast is it growing? Get this. A major new study by Germany's Institute of Energy Economics, the EWI, is projecting a 6-fold increase in installed capacity, and that's just by 2030. That is an insane rate of growth. And what's really interesting is where they're getting this free heat from. You know, the early projects went for the obvious stuff, like waste heat from a nearby factory. But the new wave of projects is getting way more creative, pulling heat directly from rivers, from lakes, and even from the sewage water flowing right under our feet in the cities. But, okay, it's not all smooth sailing. There are technical limits. This chart kind of lays it out for us. For district heating, where you need water up to about 100 degrees Celsius, the tech is totally mature and ready to go. But for some heavy industries that need much, much hotter temperatures, we're talking over 150 degrees, the technology is still really in the pilot stage. Pushing that temperature limit is the next big frontier.
Okay, let's talk about the money. Because as you can imagine, building these behemoths costs a fortune. And a brand new, groundbreaking study from that same EVI Institute has just revealed a very surprising and very important reality about those costs.
You have to understand, for the longest time, trying to pin down the real investment cost for one of these massive projects was basically impossible. The data just wasn't there, it wasn't transparent, and different reports give you completely different answers.
And this is what that chaos looked like. I mean, just look at this chart. Every one of those lines is a different cost estimate from an old study. For the exact same size of plant, say 20 megawatts, you had estimates as low as a few million euros, and others soaring past 70 million. You just can't plan a national energy strategy on that kind of guesswork.
So what the EWI team did was brilliant. They went out and gathered the real data from 75 actual and planned projects. And their big reveal? Well, for one, real-world costs are significantly higher than a lot of those older, more optimistic guesses. They also found that often the biggest cost isn't even the heat pump itself, but all the other stuff, like drilling or connecting to the river. The good news, though, is that as the market grows up, the costs are finally getting more predictable.
But hold on. The financial cost isn't the only hurdle here. There's another one. Those special fluids running around inside the machines, the refrigerants, they come with their own unique environmental challenge. This gets us into the weeds a little, but it's super important. The problem of refrigerants. A lot of the traditional ones are synthetic chemicals called F-gases, and they are a climate nightmare. They have what's called a massive global warming potential, or GWP. That means if even a tiny amount leaks, it can have thousands of times the warming effect of CO2. Thankfully, the whole industry is now shifting towards natural alternatives, things like ammonia or even CO2 itself, which have a tiny GWP. They do bring their own engineering challenges, but it's a huge improvement.
And there is a silver lining here. The EWI study is actually pretty optimistic on this front. They point to tough new rules like the EU's F-gas regulation, which are forcing this change. And they note that because of this big push towards low GWP refrigerants, even as we build thousands more heat pumps, we might finally break that upward trend of these specific emissions.
So it all comes down to this. Germany is betting the farm on these giant machines to clean up its heat supply. We now have a much clearer, much more realistic idea of what they actually cost to build. The technology works, the will is there, but the scale of this challenge is just immense. The question isn't really if they work anymore, it's, with the real costs finally on the table, can they be built fast enough to win the race against time?